Hello viewers, welcome to CEC lectures. Myself Dr. Preeti Jagwani. I am from Department of Computer Science, Aryabhat College, University of Delhi. So as you all are aware that presently we are going through the series of operating system concepts, and in our previous lectures what we have seen, I'll just recall it in a nutshell and then we'll formally begin with today's lecture. So in the previous lecture what we have seen is what actually an kind of computer system, and within that system what is the where actually this operating system stands. So this is basically a kind of I can say it's a system software. We have seen categorization of softwares. Within that system software we have seen, and within the system softwares operating system is one of the major I can say components. Then we have also seen what actually this operating system is. So in a kind of single line I can say this operating system works as the manager for the all resources of computer system. And today what we are going to see is basically what is the internal organization of the computer system and how operating system interacts with this internal organization, or what is the role of operating system in the whole management. And also we will be covering some interrupt handling, which is an important part of operating system dealing with the internal organization of computer system. Now coming to what a computer system consists of or includes of. So basically a general purpose modern computer system, what we can say, basically consists of processors. It could be one processor or more than one processor, depends on is your machine is a single processor system or it is a kind of multi processor system which is dual core or something of that sort. So it could be one processor or more than one processor. Then we have a number of device controllers. I'll be coming to what actually this device controller is, and all these device controllers are actually trying to access to the memory, and the way through which they are going to do is a common bus. So basically these device controllers are connected through a common bus, and that bus provides the access to the shared memory. So here when I'm talking about shared memory, I'm kind of specifically I can say I'm talking about random access memory. So here is a figure which you can see. So this is only the kind of a macro view of a modern computer system which is relevant from the point of view of study of operating system. So here you can see we have CPU. Now it could be, as I told you, it could be one or more than one, single or multiple processor systems. Then whatever devices we have, for all those devices we have corresponding device controllers. So for example we have hard disk, which is lying second in the line, so you have a disk controller for that. Then you have input output peripherals which are kind of, let's say, mouse, keyboard and printer, and there are USB controllers because these are attached to the USB thing, so there are USB controllers, and monitor is also having a graphic adapter. So basically, and if you can see in the figure, these are connected to one common bus which is shown by a line, and this one common bus is actually a way of accessing the shared memory. So the devices, corresponding device controllers are there, and these controllers as well as kind of your CPUs and many other components are going to use this memory. So we'll also be seeing that how this memory is accessed, what is the way through which these device controllers access the memory. So going further, we can say each device controller, as I told you, is in charge of a specific type of device. So for example we have disks, so correspondingly we have disk controllers. We have audio devices, so corresponding controllers. Video displays we have, so corresponding adapters or controllers also we have. And the CPU and these device controllers execute in parallel. So means one instruction is being kind of we can say executed by CPU, and others some tasks are also also being done by device controllers. So it is something that the CPU and the device controller can operate in parallel. Now, what is the kind of, I can say, a bone of contention here is actually the memory cycles. Your CPU and all your device controllers need to compete for memory cycles, because I have already told you that these device controllers are going to use the memory with the help of a bus, which is kind of a shared bus. So basically they need to compete for memory cycles, and obviously if there are kind of many components which are looking for one particular resource, there is going to be a conflict. So in order to solve this conflict, so now the question arises, if there is a conflict, who is going to solve this? If this conflict, as this conflict is about the memory cycles, there is a memory controller which is present to synchronize access to the memory. So I can say memory controller is the component which is going to solve this conflict of memory being asked by CPU as well as by the disk controller, and these disk control, not only disk controller but the device controller. So CPU and device controller are operating in parallel, and because they are operating in parallel, they need to have memory at the simultaneous times, and if they have access to memory at simultaneous time through a shared bus, there is going to be a conflict, and this conflict is being resolved by the memory controller. Now let us try to understand. Till this point what we have seen is what is the organization of computer, a macro view I can say, and the view which is only relevant to the study of operating system. Now with this background, I can say what happens when a user starts or switch on the computer. So a user switch on the computer until you get your kind of, I can say, operating system interface, or in a layman term I can say desktop. So right from switching on the button, that starting of some process which you can kind of I can say witness on the screen, till getting the desktop ready where you can execute your commands or whatever you want to do, you can process that. This whole process is starting from switching on the button till getting the desktop is known as the process of booting. Now what actually happens within this process of booting? So I can say system, when it is being powered up or when it is being restarted, rebooted, it requires a simple initial program to run, and that program is known as bootstrap program. Now two questions. One is, where is this bootstrap program kind of residing? Second question, what does this bootstrap program do? So the answer of the first question lies in the term which we explored in the previous lecture, or I can say in the first lecture of our operating system concept series, and the term is firmware. I have told you that firmware is an essential component of the computer system along with liveware, software and hardware, and that is basically something, I can say, some hardware chips on which some kind of software or some kind of program, some kind of instructions are, I can say, hard coded or embedded. So here your bootstrap program is going to be stored within the ROM, which is read only memory. It is a it is a read only memory, and you cannot write it on again and again, neither it is volatile, or it could be stored on EEPROM. So EEPROM here is a, I can say, these are here firmware. So EEPROM is electronically erasable programmable read-only memory. That is the full form of this, electronically erasable programmable read-only memory. So this bootstrap program is going to be reside inside this firmware. So that's the, I can say, answer to the question number one, that where this bootstrap program resides. Now the second question comes up, what this bootstrap program is supposed to do. So whenever you are going to boot a system, whenever you are going to switch on the power button, this bootstrap program is kind of the main execution entity here. It initializes all the aspects of the system, from CPU registers to device controllers to memory contents. All the aspects of systems are actually kind of, we can say, are initialized with the help of this bootstrap program. So basically I can say this bootstrap program is a set of instruction which is used to initialize all the aspects of the system, and this bootstrap program is residing inside the firmware, ROM or EEPROM. Now the task of this bootstrap program is to load the operating system. So whenever I am saying load the operating system, what does it mean? Now first thing, you need to be very careful that whatever your system is accessing, whatever data, whatever program, whatever instructions, whatever programs, whatever softwares your system is or your CPU is accessing in any way, they are to be stored inside your random access memory, the RAM. And so is the operating system. So getting the desktop screen is desktop is a part of operating system. So getting that interface screen, either it could be desktop or any other screen. So getting that kind of interface screen from which through which user can interact with the machine is that screen or kind of that part, that desktop is a part of operating system. So basically what is happening till this time is your operating system is being loaded into random access memory. So from where it is coming? It is coming from hard disk. It is stored in the hard disk, and from hard disk it is being loaded into the random access memory. So to put booting in simple manner, I can say loading of operating system into random access memory or into memory is also known as booting. But this is the process of booting is much more than just loading of operating system. Now who is responsible for loading the operating system from hard disk to random access memory? It is none other than your bootstrap program. So your bootstrap program must know how to load the operating system and how to start executing that system. So basically your bootstrap program in a way is going to look for the operating system kernel and load that into the memory. Now if you can recall our previous lectures, our operating system is divided into kind of two major portions. One is the core part, which is kernel, and another one is kind of, we can say, system programs. So kernel is being loaded by bootstrap program. So now once your kernel is being loaded and executed, I can say your system is ready to provide the services to its user. Now the next question arises, is it only the loading of kernel into the random access memory which is sufficient, or all the services will be provided by just this kernel? If answer would have been yes, then the next question arises, why do we need another components which are system programs and so on and so forth, which are outside the kernel? So kernel is not there to provide all the services. Some services are provided outside the kernel by system, and that is by system programs, and these system programs are also loaded into the memory at the time of booting, and whenever these system programs are loaded into random access memory, then they become system processes. And we have another term which is known as system daemons that runs the entire time the kernel is running. So now we have three components. One is kernel, another one is system processes, and the third one is system daemons, and these all are being loaded into the random access memory while your booting is going on. So now we can say booting is your system is kind of getting ready to take your commands. And how it is getting ready? By providing an interface in the form of an operating system, and this operating system is lying somewhere in the hard disk, and your bootstrap program is responsible for loading a copy of operating system from hard disk into the random access memory. So now your machine is booted. That means your machine is actually ready for, I can say, taking up your instruction. Now what happens inside the system after booting? So after booting, a user is going to kind of give some commands. So these commands are going to kind of, let's say, trigger some event. So for example, as a user, I need to print some let's say word files. We are taking very simple examples here. So this print command is going to ask for the occurrence of an event which is related to the output device printer. So now how your computer system is going to handle that? So whenever there is an occurrence of an event, a signal is being occurred, and that signal is known as interrupt. So basically your interrupt is a signal for occurrence of an event. So why we are going to say this as an interrupt? Because the normal functioning will be kind of, we can say, stopped for some time, later it will be resumed. When you have an interrupt and that interrupt is handled, and after handling that interrupt, your normal this thing resumes, normal processing resumes. Now who can kind of, I can say, initiate this interrupt, or who can generate this interrupt? The interrupt can be generated either from the hardware or from the software. So your hardware is going to trigger an interrupt at any time by sending a signal to the CPU, and this signal is going to travel by the way of system bus, and we have already seen this system bus in our previous figure. Now what about software? When it is an interrupt which is to be generated or which is to be triggered by operating system, this operating system is going to trigger an interrupt by executing a special operation, and that special operation is known as system call. This system call is also known as monitor call. So when your hardware is going to issue an interrupt or is going to trigger an interrupt, that hardware is going to trigger the interrupt with the help of a signal which is being sent to the CPU. As far as software is concerned, it is going to trigger the interrupt by executing your system call, which is nothing but a special kind of operation. So now after booting, whenever an kind of event is occurring, there are some interrupts which are generated. Now computer, what next? These interrupts are to be handled, and each computer design has its own kind of, we can say, interrupt handling mechanism, which may be very which may be different, but there are some underlining functions which are common. Now in order to it is also very necessary that in order to we can say have the desired speed, these interrupts must be handled very, very quickly. So these interrupts are required whenever generated, whenever triggered. These interrupts are required to transfer control to the appropriate interrupt service routine. So that means, let's try to understand this mechanism in this way. There is an event which is to be triggered, and there is a corresponding interrupt which is to be generated. Interrupt is triggered either by hardware or by software. Now after getting generated, this interrupt is going to transfer the control to the corresponding interrupt service routine, and within that interrupt service routine we have a straightforward method for handling this transfer. Now whenever your interrupt generated is transferring the control to interrupt service routine, the simple and straight method for handling this transfer would be to invoke a generic routine to examine the interrupt information. So now that interrupt information has to be examined, and the corresponding interrupt specific handler will be called. So we have interrupts and the relevant or related interrupt specific handlers. Now, as I told you, in order to maintain the speed, we need to have we can say handling of interrupts is to be done quickly. So what will be the quickest possible way of handling the interrupts, given the number of interrupts are predefined, limited, and the corresponding interrupt service routines are also predefined and attached, we can say. So since there is a predetermined number of interrupts which is possible, the quickest way to handle this situation is to use a table of pointers, and these are the pointers. So this is basically a data structure, I can say here, which is used to handle the interrupt or which is used to handle the interrupt with the help of interrupt routine. So there is a table of pointers, and these pointers are pointing towards interrupt routines, and this data structure will be used in order to provide the necessary speed. And interrupt routine is in turn called through the table with no immediate intermediate process needed. So in this interrupt I can say interrupt table, we have interrupts written one side and the corresponding pointer to the interrupt service routine. So whenever an interrupt is evoked, the pointer is pointing towards that particular interrupt which is invoked or which is triggered or which is generated. The corresponding interrupt routine is directly called through the table, and we don't need any intermediary module to be operated here. Then this the question arises again, to have some speed, we need to make sure that this table of pointers is quickly accessible. So this table of pointers is stored in some initial slots of the memories of 100 or so locations, which is basically, we say it is the low memory area, in order to access it very fast. And these locations, these low memory area locations, are going to hold the addresses of those interrupt service routines which are required for the operation of various devices. And this table or interrupt vector, this is also called, or this could be an array also, and this is an array of addresses which is better known as interrupt vector. This array or interrupt vector of addresses is then indexed by a unique device number which is given with the interrupt request. So for example, I am giving just an example. For example, the number of printer or the index number of printer is, let's say, 001. So whenever an interrupt is generated which is having the request for printing something, this number, this unique device number which is 001 is going to be I can say be into that interrupt request. And because of the indexing by a unique device number given with the interrupt request, it is very fast to access the address of interrupt service routine for that particular interrupting device. And if the interrupt routine needs to modify the processor state, for example, processor is working in state X with some of the registers, let's say R1, R2, R3 having some data, and suddenly an interrupt comes up, and this interrupt needs to modify these register value. So before modifying this register's value, the previous state has to be explicitly saved, so that after completion of interrupt, that state can be revoked and the normal functioning of CPU can be resumed. So it must explicitly save the current state and then restore the state before returning, and this way we can say your interrupt is going to be serviced where the saved return address is loaded into your PC, which is the program counter, and the interrupted computation resumes as though the interrupt had not occurred. So basically CPU is operating in one state, an interrupt comes up, quickly handled, the state is being I can say restore, the state is stored, interrupt service routine is completing its work, and after the interrupt, before the interrupt returns, it resumes the whole state of the CPU. So this is the whole process through which your interrupts are working. So let me summarize this lecture. Here we have started from what is the macro view which is required for the study of operating system concepts, and there we have seen the concept of shared memory as well as some device controllers, and also we have seen how this interrupts are going to be handled, and here is a list of references which is being used for preparation of this lecture. Hope you had a fruitful learning. Thank you.